Our unit on circular motion is going to deal with just uniform circular motion. So the question is, what is uniform circular motion? So when we're talking about uniform circular motion, we are going to say that the object is going to have a constant speed, but yet the velocity will be changing because it's changing direction. And we'll explain that a little bit more. So, a couple questions to get started. Can an object be accelerating if its speed remains constant? The answer is yes, it can, because its direction is changing. As long as the direction is changing, it's accelerating. So acceleration can deal with the change in speed or the change in velocity, or both of them. So the next question is, can the object be accelerated if its velocity remains constant? The answer would be no, because that velocity is a vector quantity. That would mean if the velocity is constant, its speed and direction are staying constant. And we know as we look at something traveling in uniform circular motion, the direction is constantly changing. Here's some examples of just different pieces of equipment that are exhibiting uniform circular motion. So we'll just look at a few examples that we are familiar with. Planets spinning on their axis, CD disk, or it could be the moon orbiting the Earth, or it could be even satellites orbiting the Earth. Those would all be examples of uniform circular motion. Their speed is going to be constant, but the direction is going to be changing. So we're going to look at that direction as it changes. So it doesn't have constant velocity because at every point on the circular path, the direction is changing. And so if we were to draw what that direction is, you can see that it's drawn on this diagram. It is the tangent line at that moment to the direction of what the object is moving. Okay, so if I chose this point right here, my tangent line would say that's where my velocity is. If I chose this point here, this is where my velocity is at that point. So you can see that at any point on here, if I chose this point, that tangent line, it is changing its direction. So we are always having a change in direction. And so the velocity, therefore, is changing. And if velocity is changing, then there must be an acceleration. We just want to look at some views that we have talked about different things traveling in the circular path. What direction does a spinning object have? If you were cut the string and it should fly off, well, it should follow this path right here, that tangent line to whatever the circular path is. So it should fly off and move in a straight line, because if the string is cut here, that force is then eliminated. If that force is eliminated, there is no force causing it to go in a circular path. Now, this force that we call, that makes something go in a circular path, is called centripetal force. It is not a new type of force. It is supplied by one of the other forces that we have used. It could be applied force, it could be force normal, it could be friction, it could be tension, or it could possibly be gravity. So any one of those other forces that we have are supplying the centripetal force. We do call it the force centripetal because it is causing that circular motion. So an example, a car turning around a corner. The force that's causing it to turn inward like this is the force friction. Swinging a stopper on a string, the force that's causing it to go in that circular pattern is the force tension. We do call it force centripetal, but it's being supplied by one of our other forces. And this is just talking about that car going in a circular path. It's this force friction against the wheels that's causing it to go into that path. Now, sometimes on roads too, especially on some bridges, you can tell that turn. When you go up on them, they are banked. So in other words, they're not flat. They're kind of tilted at an angle, and that force normal helps push things into the curve too, so that it will stay on the road. So this would just be an example of swinging a bucket of water. It's that force tension that would be causing the centripetal force in this case. Okay, so it's the tension in the wire or the string. The centripetal force for the moon orbiting the Earth, what's supplying that centripetal force? It would be the force gravity that is supplying that centripetal force. So as you see, I've gone through a few examples here that show that, yes, we do have that force centripetal, but it's really being supplied by another force that we are familiar with. So I just want to look at the acceleration. So when we talk about acceleration moving in a circular pattern, we call it a special name. We call it centripetal acceleration, then it's abbreviated by A with a subscript C. Now, this centripetal acceleration is equal to the velocity squared divided by the radius. If we look at the units for that, if we have the velocity squared, meters squared over seconds squared, divided by the radius, which would be meters, you can see that you really have a meter per meter. If I break it down, and you really end up with a meter per second squared, or you could say a meter per second each second. And that is the units for acceleration. So those break down to be what the units are for acceleration. So centripetal means center seeking, and it is always directed towards the center of the circular path. So this is our centripetal acceleration. So now we want to relate the circular motion to Newton's second law of motion. We know his second law is force net equals mass times acceleration. Well, if there's an acceleration when something's traveling in a circle, that means that there also has to be a force centripetal, and we're going to abbreviate that with capital F sub C. So I just rewrote the law here. Force centripetal equals mass times acceleration using acceleration centripetal. And then I broke down what acceleration could be. Acceleration is the mass times v squared over r, because this right here, v squared over r, is what acceleration is equal to. Okay? So it kind of puts those on here. So we can see that since we have an acceleration that is towards the center of the circle, the centripetal force is always towards the center of the circle, and that's what centripetal means, is towards the center. So those go hand in hand. Just like when we had this Newton's second law, whatever direction this net force was in, same direction was the acceleration, so we can hold that true for when something's traveling in a circle. So look at a problem here in your book. It's on page 308. It's a woman flying, and they want to know, they want you to give a force diagram that is quantitative, so we need to figure out a couple things here. We got to realize that this is in kilometers and this is in meters. So there's one thing that we have to do a conversion. So let's just convert this first. So don't we know that there are 1 hour is 3,600 seconds. And then we have to convert kilometers. 1 kilometer is 1,000 meters. Once I convert that, I think I got 65.3 meters per second. So I got my velocity in the right units. Okay? Now, on my force diagram here, what I have is, we're looking at her when she's upside down here. We got a force gravity. Just try to clear it out. And then she's sitting on that seat. There's also a force normal on that seat. So those two forces are really giving her the force that's applying the circular motion, the centripetal force. So I could write my equation. The force net here of those two is force normal plus that force gravity. Or I could say this force net here is really the force centripetal. And that force centripetal equals mv squared over r, which equals the force normal plus the force gravity. Okay? We know how to figure out force gravity. Remember, it's m times g. So if I put my values in, there's 55 newtons per kilograms times that negative 9.81 newtons per kilogram. That would solve this. Looks like I get a negative 539.5 newtons. Plus force normal, I don't know what that is, it's my unknown, equals, what is the force that's making her go in the circular? It's really these two forces added together are making her go on that circular path. So I could fill in for that centripetal force, it's her mass times her velocity squared, which was 65.3 when I converted it to meters per second. Make sure you square it over the radius, and the radius was 380 meters. Okay. When I do my calculation for this, now this velocity is also, I would say it's, since these forces are done, I'm going to say that's in the negative direction. So when I calculate this, I get a negative 616.7 newtons equals my force normal minus 539.5 newtons. Okay, so if I bring the 539 over, I end up getting force normal equals a negative 78.2 newtons. So on my force diagram, this is a negative 78.2 newtons, and this was my negative 539. And that's what they're asking for, is a quantitative force diagram for all of the forces acting on this person. Here's just another example problem. It isn't like the ones in your book, but it's just another example. They have a pilot flying a plane. They tell you what the speed is, circular path, the radius, and then they tell you 635 newtons is needed to maintain a circular motion. So this 635, this is the force centripetal that they're talking about. Okay, so that's what that really is. Now, we know force centripetal equals mass times acceleration centripetal. We haven't this given to us directly, but we do break that down. Can't we say it is mass times v squared over r? So they want to know what is the mass of this. So it looks like I'm going to do a little algebra to manipulate this. So it looks like my equation really comes out to be force centripetal equals times r over v squared equals the mass. I just manipulated that. Okay, and then you just need to plug in your numbers and you get what the mass is. I just want to kind of go through the units on this to say that, yeah, these units should turn out to be mass. So if I look at what the units for a force are, it's a newton, which is equal to a kilogram times meter per second squared, times the radius, so I'm going to take this times m, over v squared over r. So isn't that our v squared, isn't that meter squared over second squared? If you look at, doesn't this get canceled out by those and the seconds gets canceled out by this, you are left with the units of just kilograms for this. Okay, I think when I solved this problem, I got something like 70.55 kilograms for the mass. Okay, so you can just plug the numbers in and determine that, but I'm just going to show you how the units work out to give us kilograms. We just have to break down what a newton is. It's a kilogram times a meter per second squared.